Hi, welcome to another video. Did one of these videos a while back, how to repair Mackie SRM450 version 2 switch mode power supply. Wasn't very clear, made a couple of mistakes, so I took it down. Anyway, done another one, been on this one for days. I thought I'll do another one. I'm not more experienced with them now, so hopefully I shouldn't get anything wrong. So Mackie SRM450 version 2, version 1's got a big transformer up here, and version 2's got the switch mode power supply. So basic introduction, input down there, input amplifiers, then you've got all these op amps. Split the bass and the treble, amplify the bottom end of the bass, then you've got a band pass amplification, and then obviously treble. Here's one that's blown up. That's the treble chip. There's a horn only, horn or treble, and they're the two FETs that do the bass. So there's Class D. Hopefully you're familiar with the Class D amplifier. So they're the FETs for the bass, treble, switch mode power supply, FET for the PFC, so power factor correction, FET for the PFC booster, diode, two more FETs. These FETs run the switch mode power supply, which is all of this. That's a comparator. That's a frequency modulator for the PFC circuit, power factor correction, which sort of brings the mains power factor, brings it up to 1, so brings the phase of the voltage and current in line, but also this boosts it to from 240 to about 380 volts, and it's very efficient. I'll show you why later. So before I forget, this mains fuse, depending on whether US or UK, if this fuse is blown, never stick another one in. You will cause more damage. Should be a 3.15 amp for European UK models. If you stick another one in and there's already a short circuit, usually this or maybe these, you will start blowing up tracks, including tracks underneath. This one's actually alright up this end. So never replace the fuse until you found out why the fuse went in the first place. Take my word for it, if you change the fuse you're going to cause more damage, and who's ever going to repair it is going to charge you more money. So this amplifier was sent to me yesterday. I'd actually spotted this on eBay the other week, sort of going for £25 with a heatsink plus carriage, and I saw that. Now this is the earth, connects to the heatsink. I saw that, I thought, no way am I buying this. Once that earth has been blown up there, it only means one thing: live, so 240 volts has been shoved up the earth line, and I know for a fact, because I've had one and repaired all the chips, or replaced all the chips, if that's burnt, every single one of these chips, at least 31, plus these surface mount transistors, capacitors, will be blown up, every single one of them. And as proof that maybe they've taken a hit, hopefully you can see that chip there, the top is missing, that's blown up. And my one, these parts were okay, these are opto isolators. Look, even the top has blown off that one. The board's damaged there. There'll be tracks under components burnt, and on the back tracks have gone there. There will be other tiny ones that you can't see here, but so if you've got that, throw it away. It's not worth repairing, not unless you want to spend weeks, as I did, changing every single chip. Right, so I'm going to give you a quick intro how to repair these, or what you're looking for these switch mode power supplies and the PFC circuit. As I say, if that fuse, the main fuse, has blown, the common cause is that FET down here. That will have blown, and it usually takes out this driver and a couple of capacitors down here. If you don't get this right and the timing and frequency right, when you plug it in, it will just blow up again, blow the fuse and blow more components. So make sure you get this circuit right before you move on to the rest. What I'll do, I'll show you how I test these with a power supply. I'm going to connect 18 volts here on this Xenon diode. Hopefully you can see that. 18 volts there, and the ground for the PFC circuit and this switch mode power supply is obviously this cathode of this Xenon diode down here. There's my ground for the 18 volts, and there's my 18 volts going in on the end of that diode. I'll show you this one in a minute. And what you expect to see on this PFC circuit running correctly, probe this little hole next to A19, or sorry, that is a test point A19, but probe that hole there, and that's what you should get. This is that FET turning on, wait, turn on, and the frequency free running is roughly 79.5 kilohertz. It's not synchronized to anything, that's it free running. And you see there I've got a peak to peak voltage 14, depending on what your input voltage is. So that is the PFC circuit working perfectly. Now if some of those capacitors are blown up, you'll get runt pulses, and the frequency will shift from as low as 60 kilohertz up to 210, and if it does that, when you plug it into the mains, it's just going to blow up again. So that's the PFC circuit. That's what the waveform should look like. And incidentally, I saw from Farnell today, I got this keysight oscilloscope a couple of years ago. I've spent over £1,000 on all the software. I saw one of these today. It's a different model, but instead of the 100 megs, they're doing a 70 meg version for something like £499 plus a VAT. So it's roughly £600. You can get yourself a Keysight Technologies scope. This large screen, 2 gigasamples per second, 70 megahertz, 2 input channels, but fully upgradable. You can upgrade it to 100 megs, buy all the serial decode software and all that. So if you're in Europe, get onto Farnell's site, have a look at the newer model of this. So you can pick a scope up for, or a decent scope for sort of £600 or thereabouts with the VAT. Well, before I fully understood these switch mode power supplies, you get something like, when it's plugged into the mains, you can have, I don't know, 240 or more on one end of one of these resistors and 12 on the other. And I thought, if you've only got 12, how does this PFC driver start? Because that needs a minimum of 16. What I established is the 16 or 18 volts for this PFC driver comes from this switch mode power supply. This chip will start up at 10 volts. This then gives you the 18 volts for this. So if this isn't running properly, that will never start, because that requires 18 volts or minimum of 16. That just requires 10. So what I'll do now, with this test point down there, just A7, I'll stick a supply there. So with various resistors, that looks at the mains voltage. If it's under so much voltage, this won't start. If it's over so much voltage, this won't start. And it's done with this comparator in the middle. So I'm using this power supply at the moment. So this is running the 18 volts on that Xenon diode. So that you can see I've got 18.7, and it's drawing 40 milliamps with that circuit running. Now what I'll do, so that's this PFC running, and you saw the waveform. I'll start up this switch mode power supply. By putting sort of 7 volts there, it thinks the mains is okay, and this will fire up. So more than 5 volts, 5 volts as a reference comes from this chip, but so more than 5 volts this will turn on, so turn it up to 7. You see the current has gone up from 40 to 60 milliamps. That's because that power supply is now running this PFC booster circuit and now this switch mode power supply. So this switch mode power supply runs at 68, 69 kilohertz. That's the spec in the manual. If you have a look at the circuit drawing from Mackie, I can't show you the circuit drawing because it's copyright protected and maybe I shouldn't be advertising it. But this runs at 67, 68 kilohertz. This is where the frequency is generated. This PFC synchronizes to that via a capacitor. So I'll now, I've powered this up 7 volts, and now if I probe this PFC circuit again, that was running at 79 kilohertz, it's now running at 70. So it's a touch fast, but it doesn't matter. So if I turn it at 7 volts, hopefully you can see this power supply. If I turn it at 7 volts off, you can see it jumps back up to 79. So it'd be 79, 80, 84 kilohertz for the PFC, doesn't matter. But when that switch mode power supply comes in, the PFC must synchronize with it. So that's 7 volts, nothing, 7 volts, nothing. So 79.5 kilohertz, turn the switch mode power supply on, 70 kilohertz. So touch fast, but it doesn't matter. That is now the waveform of the PFC circuit synchronized to the switch mode power supply. So now I'll show you the waveforms on the gates of these under here, the 2 FETs that drive the switch mode power supply. I'll show you the gate voltage, one there and one there. These are driven by these SOC23 transistors. So if I probe that one, you cannot repair these properly and reliably if you haven't got a decent scope. So if I turn down the trigger, that's one FET for the switch mode power supply. You see 70 kilohertz, peak to peak, 10 volts. Now if I move to the other FET, see it's slightly larger. Now this little glitch down here, that is actually turning off when the other one's turning on. So I think these gates can't turn on at the same time, otherwise it would just destroy themselves. But this, when it's actually running off the mains, this disappears and it rises up. One rises up to 400 volts, the other one stays with down 10, 20 volts reference to ground. If you want to know why the other one rises up to 400 volts, have a look at my video on bootstrap capacitors. So this hasn't got a FET driver as such with high side, low side driver. So one's a high side, one's a low side. Doesn't need it because it's got this transformer. This switch mode power supply drives one coil in here, and then 2 coils drive the FETs. With 2 independent coils, one is allowed to rise up as it turns on. And you'll have sort of 400 volts, 440 volts on the gate with reference to the source, which has risen up from 0 up to just under 440 volts. So you still have a couple of volts between the gate and the source. So that's what that is for. Right, so over the back here, you've got 2 regulators, plus minus 15 volt, because all the front end amplifiers want plus minus 15 volt. That's what these are for. You've got 2 diodes down here, probably can't see them. They rectify 2 lots of power from this for the plus and minus 15, so that you get plus and minus 19 here, minus 39 here on these 2 diodes for the treble chip, plus 39 here for the treble chip. So that's the treble taken care of. And then down here I've actually stuck a 5-watt resistor on these diodes at the moment, because every time I take it out, put it on a bench, these get bent. So these 2 high-speed rectifiers, in the middle you've got plus 75 here and minus 75 on the other one. I know it's hard to view, but if you're repairing these, you'll get the gist. That's obviously the speaker output, bass here, treble there. And in case you've been wondering what this is, if you're not familiar, this is actually, I forget the value, but it's a large value coil. Wonder if it's oil cooled, but these get hot. And this, because it's a Class D bass amplifier, this stops the sort of 300 kilohertz running out to the speaker, or certainly reduces a lot of it. This 12-volt regulator drives these FET drivers down here, and this NOR gate. Trouble with measuring this, the earth of this is tied to the minus 75 volts. So that is minus 75 volts with respect to a normal ground. That's tricky when you start measuring this and having faults around this circuit. This NOR gate adds the square wave for the Class D to the FET driver. This is FET driver that drives the two base FETs, high speed rectifier, high speed op amp. Yeah, so the power for this 12 volt regulator comes from a little diode in there. It does 12 volts or 14 volts specifically for this 12 volt regulator. As I say, this is tied to minus 75. This ground is minus 75. So the 12 volts here is 12 volts above minus 75 volts. So these two circuits here, you do need to power them up independently to make sure the PFC is running at the correct frequency when this isn't running. But so what I'll do, when it's all actually working and I need that power supply, the second one, for something else, I'll then take this lead off, get a 10k resistor. So from that 18 volts, I want to drop 10 volts, so at 1 milliamp, so 10 volts, 1 milliamp, 10,000 ohms. Just simply link that to that, and that gives you your sort of 7 or 8 volts down for the comparator, so it thinks there's mains, and the switch mode power supply turns on. So finally, finishing off, there's the mains input. But look, me touching that, oh, it's not 240, so it's a lot safer to work on this amp. When something keeps on blowing it up, you can obviously limit the current with a power supply. So I thought, what voltage will this work down to, knowing they work at 110 for the USA, 240 for Europe. So that's why I've got this other power supply down. It can only supply 3 amps at 50 volts, whereas this other one on the right is sort of 2 amps at 30, or you can double it to give you 4 amps, but then it's only sort of 30 volts, or 2 amps at 60 volts. But I really need something to give me 4 or 5 amps at 50 volts or more. So look, 41 volts is on current limit. So it's actually giving me more than a regulated 3 amps. So 3.3 amps, 42 volts, 4 ohm resistor. They're starting to get warm. That's my scope lead, and that's my output. I'm on 10 volts of division. So if I turn the volume up on the amp, oh, that's my current limit on the power supply. Right, so there it's starting to clip because the power supply is running out of current, and it's only giving me 40 volts, so I'm up at, look, 32 peak to peak, but obviously the amplifier needs voltage as well. I can get that 40 volts out on the base driver. So if I turn the volume down, or turn the input down, so I'm on 50 millivolts input, turn it 50 millivolts down to stop it clipping, 46 millivolts in, 30 volts peak to peak out, sine wave, 28 hertz. So I set this at a low frequency to give you a demonstration actually of the Class D. So you can see I turn the frequency up, and I've gone through this before. This is the base amplification, amplifies frequencies at 30 to 120 hertz more than the rest. Let me turn it down, 20 hertz. Right, now I'll show you the Class D signals, where the square wave is mixed with this 20 hertz sine wave. And there's the signal of the square wave, Class D. So all those base FETs have to do is turn hard on plus 75 and minus 75, hard on, hard off, with a frequency which is the same as this incoming frequency. You've got standard on Mackie, say 430 kilohertz to 450 kilohertz. This is actually running slow, not looked into this frequency before. This is running at 290 kilohertz, and that large metal can that gets hot will take out this square wave when it goes out to the speaker. But here is my oscillating 20 hertz input being mixed with that square wave. So if I turn this frequency up, I can't turn it down because the amplifier doesn't really see frequencies of less than 20 hertz. You can see I'm down to 11 hertz and it's not switching anymore. That's just being run through the speakers now. So that's oscillating 17 Hertz, 17 times a second. 24 times a second. 30 times a second. That's now the problem with my power supply, but don't forget this is still running off 40 volts, not 240. If I expand that out, that's all those FETs have to do. Turn hard on plus 75, hard on minus 75, and give us that frequency there. And then the square waves filtered out at the end. That's how this Class D on a Mackie works. Well, it's actually how all Class D amplifiers work. Modulate the frequency with a square wave, so those FETs just turn on and off, nothing else. That's why the FETs are so efficient. They've just got to turn on and off and not do anything else. And in case you're wondering why I'm probing, that's the output of that FET driver. So that square wave is mixed with this NOR gate. And it's actually, I can feel a lot of heat coming off here because this switch mode power supply is working overtime with only 40 volts going in. It's probably cooking. Yes, that's red hot. So, to reiterate, 45 volts. Well, so the current must have dropped a bit, but 45 volts, 3.4 amps. You can see, look, this must be starting to draw less current because the constant voltage is starting to come up. So it's coming out of current limit, which is constant current. I haven't, yeah, that's the max current is on max. And this power supply is probably getting hot too. So that's it. PFC circuit, switch mode power supply circuit. I believe this comes in first, then gives us the 18 volts to run this. Don't forget the FETs under there. This is the correct way to put it back together. Lay that over the FETs, clamp it down, and that sits underneath there. 2 base FETs, treble chip. That's a feedback resistor from the output, which is fairly hot. Yeah, 12 volt regulator, then a 5 volt regulator down there, but they're derived from the minus 75 volt rail. You look at the circuit drawing, it starts getting very complicated, but once you've worked on it a few times, it does become easy. But you know, I didn't design this, so when you're trying to fix it, you've got to work out how the circuit works first. Got to know how it works to understand it. Before I go, if you've got a valuable amplifier or valuable speaker, and you don't want this sort of thing to happen, check the mains at your venues. You can get little 13 amp adapters, plug them in, 3 LEDs light up, tells you the earth, live and neutral is in the right place. This guy clearly didn't do it. Yeah, this board, this is trashed. I'm not going to bother repairing it. Let's see, look at all those, like rectifier and the FETs from the back, and that's a plus and minus 75 down there. And to reiterate, if that fuse is ever blown, do not stick another one in. You'll cost yourself more money. I can't answer all your questions if you've got individual faults. This is just a brief oversight into the function of an SRM450 version 2. Hopefully it's helped. Thank you very much.